Welcome back to my channel, and today I'm going to solve an IMO 2024 problem. So this is from IMO 2024 problem 2. The question is as follows: for which pairs of positive integers a and b, this sequence, the GCD of a to the power n plus b and b to the power n plus a for n from 1 to infinity, is eventually constant. So that basically means after that basically is eventually constant basically means there exists m such that for all n larger than m, the GCD of an plus b and bn plus a is equal to the GCD of an plus 1 plus b, bn plus 1 plus a equal to GCD of an plus 2 plus b and bn plus 2 plus a. And this would be true for any basically n larger than n, right? I can just continue this for any value larger than n. So this is basically what eventually constant mean here. And the question is asking, okay, find all pairs of a and b such that this condition here is satisfied. Okay? And so I can actually rewrite this and say, okay, this is equal to GCD of a to the power k plus b and b to the power k plus a for all k larger than or equal to n. And obviously this doesn't have to be true for all pairs of a and b. And the question is basically asking us, okay, find all the pairs such that this is true. There is a trivial case here. This is a trivial case that when a is equal to b equal to 1, then GCD of an plus b and bn b to the power n plus a is actually equal to 2, because all these terms here are all of them equal to 2 for any n. And if I forgot to mention, GCD here basically means the greatest common divisor. And so, for example, GCD of 2 and 2 is 2, GCD of 2, 4 is 2, GCD of like 3 and 2 is 1, etc. Right? This is the greatest common divisor of a and b of two numbers. Is called the GCD of a and b. And so that's all we need to know to understand this statement. But in order to solve this problem, we need a couple of well-established facts from number theory. So let me just go over the facts here. Fact: if a divides bc and the GCD of a and b is equal to 1, then a divides c. And the other fact, which is known as the Euler's theorem, is as follows: a to the power, I should actually write it in this way, m divides a to the power of phi m minus 1 for all a and m such that a and m are coprime. These are well established facts. I'm not going to prove them, but this is basically follows from basic group theory. Which states that for any group G, for any group G, a to the power order of G is equal to 1 for all A inside G. And awesome. So now let's try and solve a problem. Suppose that A and B has the property. That means for A and B, fix A and B such that A, the GCD of A to the power n plus B and B to the power n plus A is, let me actually put K here, and let's say that GCD of A to the power n plus B and A to the power, let's say B to the power n plus A. And here, let me just remove this. Let's put it M for all K larger than or equal to M. Okay. Awesome. Now let's actually do this. Let's look at this value, A to the power K plus B. Let me multiply it by A, and I get A to the power K plus 1 plus AB. And if I look at the other value, B to the power K plus A, and multiply it by B here, I get B to the power K plus 1 plus AB. And so there is one thing interesting here, that this is minus 1 mod AB plus 1, right? And why that's the case? Because, sorry, this has to be AM plus 1 minus 1, right? Because instead of AB, just write minus 1, and that's true for mod AB plus 1. And the same for this case, I have BK plus 1 minus 1. Now, if this part, if this part is 0, if this part is 0 mod AB plus 1, there's a big if here, and if this part is 0 mod AB plus 1, the right hand side is 0 mod AB plus 1, and the right hand side here is also 0 mod AB plus 1, then something interesting would happen, right? Because if this is true, then AB plus 1 would divide A times AK plus B for this particular n that I chose here, right? For this particular n that I chose here. And sorry, this cannot be n, this is k, so this is true for this particular k here, and this is also true for b to the power k plus a, and because this would follow if this part here is true, so that means if k satisfy this condition here, then I would get this one. And now I could also, how could I still simplify? Because AB plus 1 and B are co-prime, that means they don't have a common factor. And from this first fact that I had here, I would get that AB plus 1 divides BK plus 1. And similarly here, I would have AB plus 1 divides A to the power K plus B. And so this is kind of interesting. Why? Because this basically means that ab plus 1 is a common factor of both a to the power k plus b and b to the power k plus a. So this means that this would divide the greatest common divisor of a to the power k plus b and b to the power k plus a. And this is true if a to the power k plus 1 minus 1 and b to the power k plus 1 minus 1 are both 0 mod ab plus 1. Right? And so once I have this, then I have this conclusion here, but something very interesting happens here. And the reason for this that this basically would imply that ab plus 1 divides the GCD of ak plus a to the power k plus 1 in b and b to the power k plus 1 plus a. Why that's true is exactly because of this assumption here. So here, if true, I should also add here for some k larger than or equal to m. If I could find k larger than or equal to m such that this condition here is true, then I would have this conclusion also be true, right? Because this one is equal to this one by the way of we start. Awesome. So what does this mean that a b plus 1 divide the GCD of a to the power k plus 1 plus b and b to the power k plus 1 plus a? So basically means that this would divide a to the power k plus 1 plus b, and ab plus 1 would divide b to the power k plus 1 plus a. And from these two, I would arrive at the conclusion that ab plus 1 would divide would divide a k plus 1 minus ak, and ab plus 1 divide bk plus 1 minus bk. Why? How exactly I arrive at this? And the reason for this is that I had also this condition right here. ab plus 1 divides ak plus b, and it also divides a to the power k plus 1 plus b. So I just take the difference, and so ab plus 1 would divide a to the power k plus 1 minus ak. And similarly for b here. But notice that this is equal to a to the power k a minus 1, and this is equal to b to the power k b minus 1. And now we are using the fact one here, that if I have a product and one of them is co-prime with the one on the left hand side, the co-prime means they don't share any common divisor, then from here I can actually reach the conclusion that ab plus 1 would divide a minus 1, and from here ab plus 1 would divide b minus 1. And since both a and b are at least 1, you immediately see that this could possibly happen if and only if a and b are both equal to 1. So basically I'm left to show this. I'm left to actually find some k larger than m. M was such that I have this identity here for all k larger than m, larger than or equal to m. Now I just need to find k such that this is true, right? But this should be followed immediately from Euler's theorem, right? I have phi of ab plus 1 equal to 1, and I have a to the power of phi of ab, sorry, this should be b, equal to 1 mod, both of them mod both of them mod AB plus 1. Right? This is just the Euler's theorem. And so now the question is, okay, fine, I have found a value that I can plug in here, but here I also need this value to be very large, right? So here I can just say, okay, let pk to be phi of AB plus 1 minus 1. Then I would have this identity here, but the question is whether this is large enough. It has to be larger than m, or at least m, right? And that's actually not a problem. Why? That's not a problem. Why? Because I could actually come here and say, okay, I'm gonna say that a to the power of let's say L times phi of AB plus 1 is also 1 mod AB plus 1. And also, I could also say that b to the power L times phi of AB plus 1 is again 1 mod AB plus 1 for all L integer, positive integer. So I basically can, I can actually take this fact here. I could actually take this fact here and come here and change my k, right? I could say, okay, instead of letting k to be phi of AB plus 1, let's just pick k to be L times phi of AB plus 1 minus 1. Then once I have this k, it does satisfy this property for some large enough L, because this does go off to infinity if L is large enough. And it also has this property due to the Euler's theorem, so that basically I found this k I was looking for. And then once I have this, then I have this, then I have this, and all of these would also happen. Then I would actually see that A and B both must be equal to 1. And that's basically the end of the proof, right? That completes the proof. Done. Thank you so much for watching, and feel free to make any comments, ask questions, and stay tuned for future interesting problems.